Yeah, so I'm Chris. I'm a postdoc at Curtin University in Australia, and I wanted to share what I consider a great success of using Rust and radio astronomy. So we'll get started. So here on the right, you can see a map of Western Australia, and maybe you're not so familiar with Australia, but WA is quite big. And we have this telescope called the Murchison Wide Field Array, which I'll be calling the MWA throughout this talk. And it's located basically in the middle of nowhere, very deliberately. And on the left here, I have this image that's going to be kind of hard to see. But basically, my intention here is to show all of these little dots you can see make up an element of the telescope. So each one of those is an antenna. And just to, I don't know, give you better clarity on this, if I zoom in, you can still see there's heaps of these little dots around. In fact, there's 128 of those, and each of them looks like this. They kind of look like spiders on the ground. And each of those dots that you saw is one of these things we call a tile. You can just think of it as an antenna, but they're actually closer to the FM antennas that you might have on a car to receive your radio signals. Anyway, for more details, you can have a look at the MWA telescope website there. So we're using the MWA to help us detect what's called the epoch of reionization, which for short is the EOR. Basically, the epoch of reionization represents the very first stars and galaxies formed in the universe, and we want to find that. And pardon me. Our approach to doing so is to use the neutral hydrogen signature from the EOR, but just to make it short, basically the problem is at the bottom of this image is where we are, and we want to detect this signal that happened a very, very long time ago. Because it happened so long ago, the signal is very weak, but on top of that, you have the signals from everything else in between that's interfering with that distant weak signal. So for us to find the signal, we need very precise calculations, and things need to be extremely correct. And that's where I think Rust really fits the bill. So just to quickly touch on the data, basically, each one of these antennas is paired with another antenna. Well, every unique pair makes up what we call a baseline. And all of our data is formed in 3 dimensions. There's a time dimension, there's a baseline dimension, and there's a frequency channel. And every unit of each of those dimensions is 8 32-bit floats. So a typical observation has about 50 time steps to make up about 2 minutes. There's 8,000 odd baselines. There's 768 channels, and that gives you an observation occupying about 10 gigabytes of data. For us to be theoretically able to detect the EOR, we need to average about 1,000 hours worth of observations together, which will be many, many terabytes. In fact, we need to process a whole heap more data than this. So this helps to justify why we might use a programming language that's not as easy to get started with as like Python, where you have to use something like Rust to get the performance. So my approach to help my team detect this signal was to build this software app called Hyperdrive. If you want to find more details, you can scan the QR code, but you should search for MWA Hyperdrive. And the rationale came about basically because we needed a rewrite. All of the previous code that we were using was written in C or C++ or Python, and all of it was slow. All of it is difficult to install, even though we have access to supercomputers. All of them are complicated to run, and is really confusing why things didn't work. And the documentation was bad. So basically, it was my task to rewrite things to make our team's lives easier. And so I set out to make things as easy to use as possible, make sure the things were easy to install, and make sure that the documentation was pretty good. And along the way, we can accelerate our stuff with using GPUs. I'm quickly running out of time here, so I have to be quick. So basically, I wanted to highlight a couple of useful crates here. ND Array is basically giving me tracking metadata on my dimensions as I pass them around. Hi-Fi Time is probably a crate that hasn't gotten much love in the community, but has been extremely useful for really precise calculations with time. And you can ask me about the others there later. So my approach to the programming has been to make things as flexible as possible. So basically, user arguments are passed in on the command line, and everything is optional. So up on the top here, I've got an example of some clap code that basically takes user inputs, and everything gets put into a parser, and the parser gives you something that I've been calling parameters. So arguments become parameters, and parameters are the only way that you can run things. So in this case, I have some parameters, dical parameters that has a calibrate method, and basically that goes ahead and it does a bunch of stuff. I've highlighted here a little bit of scope threads to do some concurrency. So that can use the CPU or GPU in one thread to do a bunch of calculations, and in another thread, you have some IO heavy stuff, for example. So doing things this way, I think, has been really useful to ensure that things are modular and correct, but it can mean that testing is pretty tough because there can be a lot of code that you have to set up front before you can actually get to the little bit that you want to test. Say, this is the expected number of channels that you get out of doing your current method. And yeah, so there's that. If anyone has any feedback on that, I'd love to hear it. Talking about using a CPU or GPU, it was pretty direct in the end. So basically, there's a cargo feature flag that says, oh, you want to compile with CUDA? Sure, we can do that. And then at runtime, you can select the CPU or GPU, and you have access to that code via a trait. And the trait has an implementation for the CPU, which is using Rayon, or it's using the GPU, which is basically homegrown. Yep, I'm nearly done. It basically has homegrown C code and CUDA code that gets compiled along with the Rust code. Just to give you a tiny taste of our results, basically on the left is uncalibrated data, in the middle is calibrated, and on the right is some of those foreground sources subtracted. And yep, I can't explain that right now. That's what it looks like at the command line, pretty straightforward. And I'll say the punchline here. I think Rust is particularly useful for writing reliable, fast code. Thanks very much.
Thank you very much, Chris, for your talk. I was using Rust in radio astronomy. So now we have a little bit of time for questions. If you, yeah, this one that's like, one of the questions is like, what Rust CUDA library is used?
I didn't actually use a library at all. I just used, I think it was CC to do like C compiling. And that has an optional flag there to say, this is CUDA code that we're compiling. So I point that to a .cu file, and that compiles into a .a file, at least on Linux, which then gets baked into my executable, and away you go. So it was quite manual because I have to write the C and CUDA code manually, but it works.